Hello, everyone, and welcome to another wonderful day of chemistry. Today, we're going to really dive in and talk about bomb calorimetry, which is just kind of a fancy way of determining changes in internal energy. So, just to remember, if I'm going to look at the change in internal energy of a system, this means the best way to do this is to look at our isochoric heat capacities. Because if you know how to determine one, you can usually determine the other, using the idea that both will be equivalent to the changes in isochoric heat. Now, one of the problem is whenever I'm doing this, I need to be doing this reaction under constant volume conditions. So this makes use of our bomb calorimeter. Now, these are called such because they use a sample chamber that is under constant volume. And specifically, it's under constant volume while usually being heated quite intensely, oftentimes with something like a combustion reaction inside the sample chamber. Well, this means that if we are having a constant volume but increasing temperatures and pressures, if you don't build it right, it goes boom like a bomb. So thus the source for the name. However, modern bomb calorimeters are fairly robust and very rarely explode unexpectedly. So the major idea here is you're going to put your sample or your reaction of interest in this sample chamber, then which will be under isochoric conditions, so constant volume, which can then transfer volume or heat into the surroundings. Usually this is going to be water, and this is going to be in an isolated chamber. So the heat in this entire system is going to be, or the energy in this entire system is going to be fixed. We're just going to be moving it from sample to surroundings. Now, big thing here is, again, that sample chamber is fixed volume, which means that we're going to be looking under isochoric heat being transferred from one to the other. And again, that surrounding chamber is mostly going to be filled with water, and it's going to be surrounded by a adiabatic or insulated wall, where usually it's a metal wall separating the sample and the water, allowing heat to flow freely through. Then you can go ahead and when you have the reaction or the hot sample, will release the heat from the sample chamber into the water. And by using a thermometer or a thermocouple, you can monitor the temperature change in the water. And using that temperature change in the water, you can go ahead and figure out how much heat was released from the sample. However, the problem here is then we have to figure out if I got this temperature change in the water, in order to determine the changes in internal energy, I need to know these heat capacities. And the problem is the heat capacity of these systems can actually vary significantly. So we can't just use the heat capacity of the water. We usually have to accommodate for the fact that this outer wall won't be perfectly adiabatic. And so it in of itself will also take up some heat, as well as we'll be doing things like heating the metal the uh, in the bomb chamber itself. So the first step of using any bomb calorimeter is going to be calibrating the calorimeter constant. So again, big thing to note, we're often using several heat capacities. So again, the first step is always going to be determine this heat capacity of the calorimeter. This is specifically known as the calorimeter constant. One of the big things I want you to note here is the calorimeter constant here will be a size extensive property. It will depend on how much water is in the chamber. And we'll usually have units of some energy per temperature. Most common options here are going to be joules per Kelvin or kcals per Kelvin. Often kilojoules is a common choice as well. However, sometimes you will instead use the mass or moles of the water and use a specific heat capacity, which is going to be the energy per gram of water, or the molar heat capacity, which is the energy per mole of water instead. And in this case, this allows the amount of water to essentially change slightly in between samples while still essentially helping account for the container itself taking up some energy. Often a little less accurate, but still fairly widely used. And again, here, Note that we're looking at this change in internal energy, which will always be related to the isochoric heat capacity because, again, we're transferring the energy from an isochoric system, which will be related to that calorimeter constant times change in temperature, or the mass of water times the specific heat, or the molar heat capacity, or the moles times the molar heat capacity. One of the things to make note of when we're using heat capacities is oftentimes that second subscript will be left off, and you'll just be left with CV representing all three notations. In this case, the only way to tell whether we're using the size extensive heat capacity, the specific, or the molar heat capacity is to take a look at the units. And this is going to be a very common theme in this class, where sometimes the notations break down, so always pay attention to the units instead. So the major idea here is if I know how much energy is taken up by the water, I know how much energy was released from the sample. The problem here is that one of the most common uses of a bomb calorimeter is to do a combustion reaction. For example, this was the original way in which we would determine the caloric content of food. We'd put dried food items in a bomb calorimeter, fill it full of oxygen, and set fire to it, and then figure out how much energy was transferred into the water. The problem is you need a way to set fire to these items. So most of these bombs are going to be contain what are called firing leads. So this is more or less just going to be a wire that will carry an electrical current at very high temperature, which will then ignite the sample as well as often combust the leads. So these leads are going to act as our heat source, can often be used to act as the heat source for the calibration, or often also used to ignite a substance with a known combustion energy. In either case, what you can do is make sure you release a set amount of energy um, from the sample chamber and use that to calibrate your thermo or your calorimeter constant. So either way, you do have to account for the amount of heat released from these firing leads. And that can be given as the amount of heat from the firing leads is going to be based on three key parameters. First is going to be the amount of current carried by these electrical leads. So the higher current, the more energy entering the system. The second is going to be how long you let that current run. The longer you let the current run, the more energy. And the third one is the potential bias. So essentially, how many volts of energy is being carried by every amp of current. If you multiply these three together, you can figure out exactly how much energy was released by the firing leads. Then, once you use these higher firing leads, you can use this to determine how much energy entered the system. Once you have that calorimeter constant, you can then go ahead and use these firing leads to ignite a combustion reaction and use that to figure and use a combined equation to figure out the energy of that reaction. Because the sample will produce a certain amount of energy, which is going to be equal to the amount of energy uh, released from the combustion reaction and the ignition source. And together, that amount of energy was used to heat the calorimeter a given temperature. So using our calibration, we now know our CV, we measure the delta T, and we can use our former equation to figure out the ignition energy. And then this lets us figure out the amount of heat from the reaction, and then this is going to be equivalent to the change in internal energy of the reaction, which we're often going to divide by the amount of moles of substance to get a molar change in internal energy for the reaction. So a lot of equations, a lot of nuance. So let's go ahead and do an example problem. So first, we want to try and calibrate our calorimeter. We're going to do this just using the firing leads. So very commonly, a lot of these firing leads are going to be hooked up to a 12-volt power supply, which is going to often run at something around 30 amps. So in order to generate enough energy I can really heat my calorimeter, I'm going to run this for a full 120 seconds. And when I do this, I'm going to get an increase in temperature about 5 Kelvin. So using all of this information, I should be able to determine my my calorimeter constant. So first thing we need to do is figure out exactly how much energy was released from those firing leads. So again, 30 amp current, 120 seconds, and 12 volts. Now it might be a little hard to see how all of these units cancel. The big trick here is amps is going to be coulombs per second. We have seconds from the time. And volts is also the same as joules per coulomb. So using this, we can go ahead and cancel out a couple of the parameters. So again, note the coulombs cancel, the seconds cancel, and this just leaves us units of joules. So it turns out this firing lead produced about 43 kilojoules of energy. Now, using this amount of energy produced from my firing leads, I can then say, all right, I heated the system by 10 degrees and use that to determine the calorimeter constant, which is just going to be the heat divided by the change in temperature. In this case, for this calorimeter, and this is a fairly common number, for I think it's about 2 liters of water in the surrounding chamber, it takes about 8.5 kilojoules to change the temperature by 1 Kelvin. All right, so that looks great. So now we can use this calorimeter constant to go ahead and figure out the internal combustion energy for glucose, good old sugar. So if I've got 1.8 grams of glucose and I go ahead and measure a temperature change of 8.4 Kelvin, well, what's going to be the change in the internal energy, specifically on a molar basis? So the first thing we're going to want to do is rearrange our equation up here so we can solve for the heat of reaction. So we can use that same ignition temp heat that I calculated last time, assuming we're going to ignite it the same way. And then we now have our CV delta T. Again, we determined our CV from last time, and we measured a change in temperature of 8.36. So this will give me the amount of energy that went into the calorimeter, subtracting how much energy came from the ignition source. The remainder was actually due to the combustion reaction. So that gets me the heat of combustion. But note we want the change in molar energy, which should be the same, or the change in internal energy, which should be the same, but in a molar basis, we're then going to divide this by N. So again, if I have an 1.8 gram sample, turns out the molecular weight of glucose is 180. We love it when the math is easy. So this ends up with a change in internal energy of about 2,800 kilojoules per mole. One of the things to make note here is notice I threw a negative sign here. So one of the ways you can always tell what the sign is remember that this reaction should be releasing energy, so it will have a negative sign. So if you mess up your signs and reactions, don't worry too much. You can always use intuition to figure out should the system be gaining energy or releasing energy. So that brings us to the end of our isochoric heat capacities. Next time, we're going to branch out a little bit and look at constant pressure conditions. It's time for isobaric. Until then, take care.